All right, so what I thought I would do is go through a little bit about what's new in version 12.1, and people are very welcome to ask questions and so on. Uh, you know, with all of the disruption in the world associated with that little 29,000 base pair virus, it is almost embarrassing how little perturbation it's had on my life and even on our company. I think I've been a remote work at home person for 29 years now, and really doesn't make much difference. Um, I'm sort of uh, I think um, uh, as it happens, last few months I've been particularly in a hermit mode because I've been working very hard on a science project of something that we were hoping to announce just right about now, but we clearly have to put it off a bit to let the world stabilize a little bit. But it has to do with the fundamental theory of physics, and I'm really excited about it. It had a dependency. We couldn't announce it till after version 12.1 is out because the tools that we're going to make available make use of version 12.1 features. All right. Well, okay. What's in version 12.1? Well, there's a lot of stuff. This is the summary of new features. There's how many functions is it? I'm not even sure. I'm sure I say here. So this is the blog post that I wrote about it that came out this morning. And the things I'll be talking about are covered in one way or another in this post. Okay, 182 new functions. That's kind of a big deal because the total number of functions is now around 5,000. But for a 0.1 release, 182 completely new functions is quite dramatic. And that's kind of a word cloud of some of the highlights here. All right. Well, let's see. We can go through the blog post. We could go through here. Why don't we actually go through here? I'm going to, although I'll mention a few of the things that are in the blog post. One of the more significant in terms of immediate usage, particularly affecting people on Windows machines, is the support for high DPI. That's something which is like when you've got 1,000 icons and they're all bitmaps, it's a lot of work to make them all very high resolution and potentially vector, but that is now done. And so things look really crisp on a Windows machine. I happen to be running on a Mac here today, but that's one of the things we've done. All right, I think I'm going to jump into some of the new features, and I'm going to start off with some things which are kind of things related to the core language, and then we're going to get to some of the more sort of whizzy things a little bit later. So in terms of core language, we're always interested in figuring out kind of ways to make the language easier to use and more sort of ergonomic. One of the things that we introduced a couple of versions ago was the thing called nothing. And what nothing does, if you put it in a list, it disappears. It's nothing. Nothing is there. One of the things that I often find myself needing is a mechanism where I can say, let's take that list and let's say I want to replace, let's say, C in that list with XY. Now, if I just do that, I'm going to get the list XY inside there. But let's say that I want to splice. I want to make the XY a splice. So what I could say now, we have this new thing called splice, where you can just say C is the splice XYZ. And what that will do is it will auto splice into the list. It's small, but it's very useful. And the alternative to that is something where you have to kind of go from the outside and say, okay, take the thing I've got and flatten it. Okay, I see a question already on our live stream about will autocomplete be enabled in the new Raspberry Pi version? Gosh, I'm surprised that autocomplete isn't there right now. But
We can look at that.
Yeah, I would have thought it should be. Okay. So anyway, back to this. So if I have a function like select, I might say something like select, I don't know, something like this, and I might say something like prime q. That will select things which are primes there. There's also an operator form of select where I say select prime q, and then I can just give that list here. And that's convenient if you want to kind of put select in a pipeline of things. It's convenient to have that operator form. So the question is, what if you have a function that doesn't naturally have an operator form? Just some function f that is normally takes its arguments, f of a, b. It just does what it does. Okay, so there's a new thing called operator applied. And what operator applied does is it takes the function f and it says, treat that as something which is going to have an operator form. So if I do this, that turns into that. So what that's saying is it's doing like what select did. If I did operator applied, I could do that for select itself. I could say operator applied of select, and then I could give it that prime q there, and then I could give it its main payload. And what that will now do is it will make select into an operator, and it will apply it as an operator to that list. So that's what it does there. So this is just a convenient way to take any function and sort of treat it as an operator. Okay. Now, there are a lot of things like that. Another one is curry applied. So we had a preliminary version of this in earlier versions. This now is sort of a full version of this where we're able to say, let's see, we're able to just say, apply this. This is going to be a function of two arguments. It is the, actually, this is a curried form of curry. So this is saying, I'm going to make a function of two arguments. The function is f. The first argument is x. The second argument is y. So that's what it does. So if I were to, I could make this a function of three arguments or something, and I could put another one of these here, and it will know to accumulate those as arguments. So again, this is something, if you're doing functional programming, this is just a convenience that will help with that. Another one that's really kind of a nice little thing is reverse applied. So that's particularly relevant. Let's say you've got, let's say you say reverse applied f of x, y, that will be f of y, x. Okay, why should you care about that? Well, if you're saying sort, let's say a list range of 10, and then say reverse applied of, let's say, let's see, I think numerical order, that will now sort that into reverse numerical order, because reverse applied is now essentially an adverb that is modifying this verb, which is the function numerical order. Okay, so I'm sort of just getting started here. Let's see, increase magnification even further on this notebook. Okay, I can do that. Make that a bit bigger then. Okay, so continuing with sort of programming kinds of things, another function that is seems like kind of a detail, but it's a really useful thing is the family of subset functions. So like subset cases. So I might take this list here, and I might say, okay, I want what should I do? I just ask for the cases of the list x blank y blank in there. Okay, so that's going to give me all pairs of all the pairs of subsets in here. This particular version is without overlaps, but I could also say overlaps goes to all, and then I'll get this big long list of all the pairs that can occur in the subset. Rodrigo was asking, I guess, back here about splice. The reason I like splice very much, splice is specific to lists. It doesn't have any kind of slippery slope behavior of the type that that sequence has. You know, I've been trying to. I had a version of sequence in SMP, which was a predecessor of Mathematica back from 1979, 1980, and sequence was one of the sort of really bad design things in SMP, and I really never wanted it in Mathematica or in Wolfram language. We sort of had to have it, but sequence is a very slippery thing because and we've ended up with things like sequence hold, which is sort of a protection against sequence flattening and so on. Splice is a much cleaner thing. It applies only to lists, and it just does this one thing. We're discussing having a mechanism for having it work in other functions as well, but right now it just applies to lists, and it just does this one thing, and you'll never get in trouble with it. Okay, question about high DPI on Linux. The answer is yes, that is also supported, and you're going to ask me exactly what the details of that are, and I do not know, but maybe somebody else on the live stream knows. But the big issue is just building the infrastructure and building the assets to support high DPI.
The only detail I have, I think, is that it's Qt5. It's like we upgraded to a new version of Qt that supports high DPI on Linux.
Good. So it should work. So okay, yeah. As Sandra is pointing out on the live stream, one of the big advantages of splice is you can carry a splice around without it blowing up in your face, so to speak. All right. Anyway, so subset, replace, and so on. It just so happens that subset replace is a really useful function for my physics project. Just to show what subset replace would do, let's see. I might do subset replace here. I don't know, what could we do here? We could do something like x plus y, x minus y here. I wonder what this will do. This might do something. Oh, it may not be. Doesn't let you do that. Yes, it doesn't really have a well-defined way to do that. Okay, so that was just doing the picking out any pair x, y here and doing that replacement on it. By the way, it's kind of an interesting thing that subset replace and subset cases are things which happen to be really useful for my physics project, but they actually came out originally of our support of Sparkle and of semantic querying and being able to do operations on sort of sequences of sequences that you might find in a triple store of entity property value kinds of things. All right, so just going on with kind of some of the core language kinds of capabilities. Another new thing is date interval. Beginning support for that. There'll be a lot more to come. Being able to do things that I kind of have a nice physics ring to them of being able to deal with things like infinite future, and being able to say infinite future is less than today. I wonder if that works. No, that says it's false, which is correct. So okay, we have a bunch of things coming there. All right, find equational proof. That's a much more technical thing, but one of the new things there is supporting general predicate logic. So in addition to being able to do, see if we can have an example here. Here we go. This is predicate. So let's get this predicate here. This is find a proof of the predicate that Socrates, represented by that symbol there, is mortal. And then it says for all x, it implies man of x. In other words, if x is a man, then mortal of x. And then it's asking, and then it says that this for all x, this implication is true, and it's also being asserted that Socrates is a man. And so then if we run this, it will say that, yes, we can do the same thing that certainly Aristotle was able to do with syllogistic logic, and to prove that, yes, indeed, Socrates is mortal. It's a bit of a complicated proof here. We could say, give us the proof network, and it's probably a bit long and complicated. It's not really intended for humans. It's more intended for computer verification of things. But it's really nice that now we can do full first-order logic. Now, another thing that we've added is the ability to do finite groups. So if I'd said something like axiomatic theory of group theory, I would have got the generic axioms for groups. So this is saying that's the associativity axiom, that's the existence of inverses axiom, and so on. But this is for all groups. Now we can, for example, say something like, let's try this. Let's try doing the quaternion group. And so what this is doing now is it's using our data from finite group data, and which we've also greatly expanded for this version, to be able to give us actual axioms for that particular group. So I wonder if I say I'm living dangerously, because I don't actually know if it's going to work, but let's just try. I had to use this group recently. Oh, come now. Okay, so much for that. Let's see what happens if I just ask for a general symmetric group here. Oh dear. Well, so much for that idea. Well, I think if I ask for finite group data, I could identify a group in finite group data, and I could say, show me, what did I do wrong here? Well, let's just try. Oh, I just said the wrong thing here. This is I should have said symmetric group. Let's try that. Let's try the group S3, for example, see whether I can get the axioms. Oh, that's really cool. Wow. Okay, so those are the axioms of the group S3. And then from this, I can start actually giving proofs with that for that specific group rather than just generically for all groups. All right, let's jump to something completely different. Actually, I'll show you one more thing here that's kind of interesting, kind of useful, is the function time remaining. So if you have a so let's see, okay, infinity. Okay, we've got all the time in the world, right up until infinite future. So what we could do is to say something like echo time remaining, and we could say make do something like pause 0.1, echo time remaining, do that 20 times. And now let's say time constrained. Let's give it 50 times. Let's give it a 3-second time constraint here. Okay, so what we should see is this is telling us the time remaining. This is telling us how long we have left, and then boom, it aborted. Okay, so that's a useful thing if you're writing programs that have time constraints. This lets you control that. Okay, let's move to a completely different topic. I want to talk about something, a more crowd-pleasing kind of topic. Let's talk about video. So this is a new thing. It's kind of still a bit experimental in this version, but we are adding the capability to put video into notebooks and to do video computation. So let's take, this seems to be our characteristic example. It is a cheerful story. Oh, that went to full screen. Okay, not quite what I expected. And now, how is it playing? That's not quite what I expected there. I think this is confusing my system. Open with my default video player, and who knows what my default video player is. Let's just see what happens if I say video play of that video. Let's see what that does. Okay, let's see what happens here. Lovely, but where's the video? Help! Oh, that's lovely. Stop! That's what I get for... That's very loud as well. Okay, we got a bunch of bugs here. Okay, first problem that I have is stop. Help! Okay, this is amusing, but not so. Sorry it's so loud. Okay, hold on. Let me just. That's just something different. Please that probably stop playing in your ear. Sorry about that. Deleting the output made no difference. Right. Very cheerful sounding. Okay, finally, we're stopped. Okay. Good. Okay. All right, let's just debug this for 1 second because I want to show you this capability, and it's kind of upsetting if it doesn't work. Okay. All right.
The example you may want to try is the
hold
video.
On. I don't have my audio set correctly. Just a second, please. Go ahead. Yes.
You may want to take a look at the video play ref page. There's a good example there.
Yeah, I understand, but what happened is the thing got set to the wrong default video player.
Right. So there's one external video player that does videos, and then there's one that you have right now that plays in the notebook itself.
Right. Well, it's more fun to show the one in the notebook, but let's I don't know why it's playing external to that. Well, let's do this one. Okay, well, it's the same dramatic llama, but let's see if we can. All right. Oh, let's just do video play of that stream.
Well, you need the dynamic, the cell with the.
Okay. Why isn't that stopping? Stop it. Sorry, guys. Okay. Listen, you know what? Let's get this debugged, please, and get somebody to get the right video player here and get this nonsense, and we'll come back to video. It's very cool, and I'm sorry it's so loud, and that also needs to be adjusted.
Well, I think you need a dynamic cell as well. No.
I'm not going to use that. I'm going to get this to work correctly. But we will come back to this. Apologies, everybody. All right, let's go back. Okay. Okay. All right. Well, let's go to a completely different topic. Let's talk about some math. I'm keen to show you video because it's cool, but we can yeah. Let's talk about some math. All right. Let us talk about this function asymptotic. So the goal of asymptotic is to find asymptotic estimates of things. So actually discrete asymptotic has to do with finding asymptotic estimates of discrete things. So I ran into this function called Bell B, which is a Bell polynomial. And we can now ask, what is the asymptotic expansion? Oh, great. It's not very helpful, is it? What is the asymptotic expansion? Okay, it's a very exotic asymptotic expansion of that. So roughly, when you make something like a power series, let's say we say series of e to the x from 0 to 10, great, okay, we have a power series expanded in powers of x. But some things, like this, there is no power series expansion. For example, we might do this, let's say it's for a factorial. What's the power series expansion of a factorial around infinity? No, it doesn't have one, but it does have an asymptotic estimate around infinity, and it's about that. So we can probably do that to higher order. We can start seeing the asymptotic estimate of the factorial to higher orders here. So there's a whole kind of way of approximating functions as asymptotic series and asymptotic approximations, and that's what we're now supporting here. So there's a collection of things there. Another area, sort of again fairly deeply technical, has to do with convex optimization and dealing with things like geometric optimization. And I'm afraid that this is one of these things where the minimal examples are already fairly complicated. I mean, this is an example. This example is sort of a classic thing of dealing with minimizing 1 over width times height with certain constraints on width and height. So like, for example, let's put a particular constraint in here that will tell us what minimizes 1 over width times height with these constraints on width and height. What's interesting about all of these capabilities, and we now have sort of a complete set of these convex optimization capabilities, is that they are they work for both small problems and really large crunchy problems. I think I may have some examples here of that. The other thing which is significant is that in addition to working over just real numbers, we now have efficient convex optimization over mixtures of integers and reals. So, for example, if I do that computation and I say what's the optimum of that function with this constraint, I could say what is it with x over reals, and I'll get some answer that's minus whatever it is here. But now if I say constrain x to be an integer, then I'll get this result here. And we're able to kind of seamlessly deal with both the real case and the integer case. Let's see. So let's see, going back to other math kinds of things. Okay, we have a continual march of more and more elaborate kinds of special functions. The news of this release is Hoyne functions, which are things that have shown up in things like conformal bootstrap studies and so on. They are solutions to a differential equation with what, 3 regular singular points? Is that right? And if we take one of these Hoyne functions, it's a pretty exotic creature. It has, how many parameters does it have? Let's see. I just keep typing until fgx. Oh, that must be enough. Okay, so there's our Hoyne function, and if I say, give me a power series expansion of that for x, let's live a little bit dangerously. Okay, there's any function that has 7 arguments, you know, is kind of complicated. But what's interesting about this function is it's showing up in a whole variety of places in physics, and it's sort of the next generalization of things like hypergeometric functions. Okay, next part of our story, vector plotting. So, one of the things I don't know I've noticed from like in my distant past, I was involved in doing things like fluid dynamics computations, and I'm sure I could probably pull up an example here of what happened when I tried to make kind of vector plots in let's see if I can pull up an actual example. The let's see. Yeah, there we go. This is from a distant past, a different life, but 1985. I think this probably has. Okay, there we go. There are some examples of vector plots, and it's kind of a nuisance because there are vectors there, but you can't really kind of see where the vectors are going. You either get to see the direction, or you get to see the magnitude, or all the arrows are on top of each other. So one of the things that we sort of solved in version 12.1 is a good way to do vector plotting that allows you to basically use a combination of scaled colors and a good alignment of arrows to give you a better way to visualize vector kinds of things. So we can let's see what happens if I abuse this in various ways. We should still get a nice visible version of this. I wonder what happens. I'm just going to try this just because I'm curious. Let's see what happens if we go to 3D. Okay, not great, but not too bad of visualizing what's happening in a vector function in 3D. Okay, so also in visualization, we added in version 12.0, we added finally sort of nice automated complex plotting. We should have here things like, okay, that's complex vector plot. That's kind of interesting because you don't have to specify very much. That's a complex vector plot. Let's live more dangerously. Let's do z to the z. Okay, that's a bit more of a mess. And let's do that plot points arrow. There's no plot points. What is it called? What is it? I should read the documentation here. Oh, it's probably vector points. Yeah, good point. Okay, so let's do that. Okay, that's a nice rendering of z to the z. Actually, I'm curious what it looks like if we just do a complex plot of z to the z, what that's going to look like. And that should, okay, there's the branch cut at negative real axis. If we want to, this is now stuff from version 12.0, but that's the z to the z in rendered in 3D there, with the magnitude as I think that's using the height is the magnitude, and the color is the angle. So now we can also do, let's do this. Let's do a some kind of complex. Let's try this. Let's try a complex region plot. And let's say z to the z is greater than, let's say, 1 over z, just for, oh dear, terrible, terrible. All right, let's do z to the z is greater than cosine of z. Also, it's getting confused by that. All right, let's do sine 2z is greater than cosine of z. And why is it saying that? Oh, because these are complex things. Yeah, silly me. Couldn't possibly have worked. Okay, so let's say real part of that is greater than imaginary part of this. Now we have something that could work. Okay, there we go. So that's now our complex. That's now, and let's maybe make that a parameter k, and let's make a manipulate here that tries to look at this. Let's say k from 1 to 5 or something. I don't know what this is going to do, but this is now looking in the complex plane. That's kind of cool. That's looking at that set of constraints in the complex plane. So complex region plot, another new thing in 12.1. Okay. Other things are things like geodensity plot. So that's doing things like, okay, you have a function on the Earth, like air temperature data. So I think we might have something here that, let's pick a city. Let's say, well, all right, this is doing, I don't know what this is doing. This is doing air temperature data around the city of Austin, and that's bringing in the air temperature data for the most recent time for all the cities within 15 miles of Austin. It might take a little while to get all of that data pulled in, and this is, gosh, okay. Well, it's pulling in all that data. Once it does that, we should be able to plot that data in a geoplot. And I don't know why this is so slow. I don't know how many cities there are within 15 miles of Austin that we have to query here. Well, let's let that run just for a second. Okay. Meanwhile, let's keep going here. Contour plots. Being able to overlay contours on top of contours of data on top of geo regions. Okay, there we go. All right, let's try running this now. Plotting that data on a geodensity plot. Okay, that's cool. All right, so we obviously we lacked some data up there, but this is now showing us a an interpolated density plot of the temperatures around the city of Austin. It seems to be quite toasty there today. I don't know if there's anybody watching this from Austin. You can confirm or deny the claim that it's colder near the river, I guess. Okay. So some improvements in contour plot 3D, plotting over regions, things like that. List plot 3D. Let's take a look at that for a second. So let's imagine that I have let's get a bunch of random, let's get a normal distribution, let's say a mean 0, variance 1. Let's get 100 random numbers, normally distributed. Now, if I wanted to, I could say something like, well, let's say list. Actually, what I wanted to do here was not that. I wanted to take, let's say 5 of those numbers, and then I wanted to say mean around, and that will give me a number with errors. Okay, so that's giving me a, let's say we pick that. Let's actually pick a random real number for that. Okay, so now this is going to give me, now I'm going to get, let me get a table of, let's say, let's just do an X there. Let's do a table of numbers where they are centered on X, but they have a distribution around X. So this is going to give me a bunch of numbers with errors. So if I now say list plot of that, I will get something where those numbers have been plotted, but with error bars. Okay. Now, one thing that's new here is that we can do list plot 3D with error bars. So we might be able to do something where we pick, it's going to be kind of a mess, but if I do this for two X and Y, and let's do this, let's say X plus Y here, and now let's say list plot 3D, see what this does. I'm not actually sure I know what this does, but let's see what it does. Okay, oh, that's just plotting the numbers with without explicitly showing the errors. If I do that, why is this not showing the errors? I'm surprised it's not showing the errors. Maybe there are too many numbers here for it to explicitly show the error bars. Oh, there we go. Okay, yeah, little error bars there. Isn't that cool? Showing the errors in 3D. Okay, on the subject of graphics, here's an interesting thing that is new. This is hatch shading. So just like you can say something like graphics of something like style of a disk and say make it purple. Okay. Now you can also say, oops, I didn't mean that, I meant just purple there. Now you can say, I don't just want it purple, I want it with hatch shading, and I want, so let's see what hatch shading looks like. That's, what am I doing here? I want, sorry, I meant hatch filling. Wrong, this is 2D. Okay, so that's now hatch filling. So that is making, when you looked at old sort of woodcut diagrams, you would often see these things where, because they weren't doing grayscales, they were doing various kinds of filling like this. So now, for example, I could do something like this. I could say, let's say, pick some random positions here, random real 10, 2, for example. Let's forget the purple, that's kind of silly. And let's make this, let's say, random real 0 to 2 pi. And this is going to define, so what this is going to do now is it's going to make this, let me make a table of 10 of these. So that's going to make these cross-hatched circles. So if I make hatch filling, okay, so let's say I want absolute thickness 0.2, 0.3, for example, and now I want the distance between those to be like 0.1. Oops, that's not what I wanted. Distance, let's say 2 or something. Okay, there we go. So now what I've got is the beginnings of my diagram where I'm using cross-hatching to indicate which circle I've got. Let's do that for a few more circles. It'll get kind of wilder looking. So this is a way of making diagrams. This is something to support diagrams. In general, we can put an arbitrary pattern in our diagrams. So for example, we have a library of possible patterns here. So instead of doing this, we could say, let's do a weave version of this. So let's say pattern filling. Oops, I did, here, let me just generate that again. Let's say pattern filling here. And let's say, now I want to say, let's make a weave pattern on all of those circles. It's a very big weave pattern. We want a much smaller weave pattern, and I guess we want some size of the object. So let's say 0.1 there. That was probably too small. In any case, we can then tell it to make to use one of these patterns. All right, I have to actually read the documentation to know how this works. To put one of these patterns, or any pattern you want, on 2D objects. Well, it's kind of the same story in 3D. In 3D, we have we can now use let's make a 3D thing. Let's say graphics 3D of a sphere. And now normally we just get a sphere that looks like that, but we can style our sphere to look, for example, to have stipple shading, for example, like Wall Street Journal illustration style. And there we have a stippled sphere. We could go ahead. There are all kinds of different different shadings. I wonder what hatch shading will do on that sphere. Okay, so that's a version of cross-hatching applied to the sphere. And in general, this is being done with GPUs and shaders and all that kind of fancy stuff. Okay. So let's see. All right. So that's more stuff in 3D graphics, variety of kinds of shading. This is just a different type of shading that you can use to get different effects. And this is all kind of in the service of kind of enhanced diagrams, sort of algorithmic diagram generation. Okay. All right, let's keep going. We talk about all right, let's talk about graphs and networks. Some of this is rather technical. But for people who use graphs, and I've been using graphs a lot in my kind of physics work recently, so I'm really excited about some of this. There are issues about multi-edges, and there are issues about ways of treating graphs that have multi-edges, that is, where there are multiple, where, for example, you would have a graph like this, where there is an edge going from between 1 and 2 here. If I say vertex labels goes to automatic, there's an edge going from 1 to 2 here. There's one that's colored red, the one that's colored blue. This is just something where there is different tagging on different parts of a multi-edge. And that's just something that in practice, working with graphs that have multi-edges, that's an important thing. Okay, so back down here, there's a lot of detailed new stuff about annotation. One of the things we've been trying to do is to standardize the way that we deal with annotation on different kinds of objects. So we've got annotation on graphs, we've got annotation on audio, got annotation on different kinds of things, and we've got kind of a general mechanism for adding annotations to things. If people are interested, I'd go over that in more detail. But let's not talk about that in so much detail right now, otherwise. All right, here's kind of an interesting thing. If we say, let's just generate some slightly complicated function here. Okay, so now let's say we can say what's the tree form of this, and it will show us the expression tree for this. But sometimes we might actually want to make an actual graph. So we can say take line 90 and just make an actual expression graph out of this. So that's equivalent to this tree form, but it's an actual graph. So for example, I could say, take that graph, make a tree plot, put it, center it, and so on. And so, for example, we could, if let's say we get some complicated algebraic expression, I don't know, we could say integrate 1 over, this is going to be kind of fun. I don't know what this is going to do, but let's just try integrate this. Let's make a table of these with n goes from, this is kind of a sketch of some algebraic expressions from n up to 10 or something. And let's just, for the hell of it, let's make them tree plots with centered trees here. And now this is going to be a kind of a skeleton representation of a bunch of algebraic expressions. Okay, that's kind of amusing. So that's showing how integrals get more complicated over as you increase this parameter as expression trees. Okay, well, let's talk about this whole interface between graphs and everything else is an important one. So here's another example. So let's say I make a Menga mesh. Let's say, I need to remember how this works. Yes, okay. So let's say I say 2. Okay, so that's a little sort of pre-fractal mesh. Okay, and if I wanted to, I could say 2, 3, I think, and that will make me the 3D version of that. And needless to say, I can go off into 4 dimensions or beyond, but let me just look at the 2-dimensional version. Okay, so now let's imagine making a graph out of this. How can we make a graph out of this? So this is kind of sort of a topological type question, and we could say something like make a mesh connectivity graph. And to make that, so take our Menga mesh, and let's make a mesh connectivity graph out of this. And so what that's going to do, in this case, by default, it's going to make a graph of every node and how it connects to every other node. Now, I think what I might be able to do here is I might be able to say, take every 2-dimensional region here and say how it connects to every other 2-dimensional region. Okay, so that's now a version of this that kind of gives us the connectivity of this mesh with respect to 2-dimensional regions mapping to 2-dimensional regions. So let me live dangerously. Let me do this for the 3D case. So for example, here, what we're going to be doing is every face of the, okay, so what this is doing, this is making a graph where every little facelet on that Menga mesh is now we're now being told how that maps onto every other one. Let's say I did it for 3 to 3. I could do then what I should get. Okay, so that's now a representation of how every little cube inside the big mega mesh cube maps. And now I could start doing things with 3D graphs. I could say graph 3D, that will now render it in 3D. And so now that's the kind of the mesh connectivity graph for the mega mesh in 3D, deduced from so the mesh connectivity and then turned into a graph. And now if I wanted to, I could do something like, let's just live really dangerously. Let's say neighborhood graph of let's say of that, and let's just do well, let's do this. Let's map that over. Wow, this is really dangerous, but whatever. Let's map that over vertex list of that graph. Okay, so what this should be doing is it should be generating all of the up to size 2 neighborhoods. Okay, it's formatting. Let's see what happens. Okay, so what this is doing now is that's taking every local neighborhood of in that Menja mesh, and it's showing me the local neighborhood of every point there. I suppose, okay, since it's by the way, I mean, we can use those kinds of things. We can use that kind of thing actually. If we really wanted to, we could say, let's do something like this. Let's say let's make a random graph here. Okay, so this is this would be like a very, very toy version of a social network. Let's do it with like 500 points here, 500 things. So this is sort of a toy version of a social network, and so we can ask a question like, for instance, I mean, the thing I just did with neighborhood graphs, I could let's just show how this works. So let's say GR is equal to that graph, and now let's say I could say take in that I could say highlight graph in the graph GR with the neighborhood graph of that around neighborhood graph around the vertex labeled 1 out to distance 2, for example. Okay, so that's now showing the sort of contagion network in the social graph of starting with node 1 out to distance 2, and I could maybe do that out to distance 4 or something, and we can see how how the virus spreads through the network. And we can also see if we delete a bunch of edges in this network, we can find out that it spreads less rapidly. The challenge is to make an accurate model of this, and that's not what this is, and that's a challenging thing. But this is at least an interesting indication of that. Just for fun, we can probably make this into a graph 3D. Let's see what that does. Okay, there we go. That's kind of cool. You can see the sort of contagion region inside the 3D graph. Okay. Let's see. All right, let's keep going here. Well, we've got various changes to graph computation. Let's not go through those in great detail. I already talked about mesh connectivity graph. Okay, let's take a look here. Something different. Let's look at geometric computation. So let's say I have the United States, USA. Okay, the USA has a polygon. And let's see, I may be living dangerously generating this. Okay, there we go. Now, let's see what happens if I say, let's just render. Is this going to work? Let's see if this works. No, it didn't work. Let's see, I think maybe what I have to do is say geographics of that. And okay, that's just rendering the standard polygon for the US. And I think I have to cheat and look at my my discussion of this. I'm sorry, it's very embarrassing. I wanted to show you. Let's see, how to get this as. Where is it? Oh, there we go. Okay. Yeah. Oh, all right. Well, okay. This is the interaction of regions with this. So, okay. So I could say just discretize region. So this is generating essentially computational geometry from the polygon that is the US. And so there we now have a three-dimensional polygon that is the US, and we could do things with it like we could say, what is the region centroid of that? And that will tell us the location. Oh, it's in meters. It's a little bit weird and not useful. That's meters relative to the center of the Earth, I think, of the center of the U.S. Just for fun, I mean, we can pick another. Let's try picking. Let's just try picking a country that might curl around a bit more. Let's try picking Russia. Okay, there we go. So that's what Russia is actually like on the surface of the Earth. That you can now do computations with as an actual 3D object. Okay. Well, let's see. I think we may have somebody here who could help me not mess up the video demonstration. So yes, if we can get Shadi to join here, that would be great. And then we can actually get it right with the setup of video. I think that's was working so beautifully when I've tested video so many times, and now as in the actual version here, it's not working. Well, maybe again while we're still waiting for that, let me talk about some other kinds of things. Oh, here's one that's interesting. This is let's try doing this. Let me try recording an audio. Let's do an audio capture. Let me record something. Hopefully this will be listening to the right microphone. Let's try. Great. Okay, we have a new GUI, by the way, for this, which I think is easier to understand. All right, I'm going to record something which is going to have various cities in it. Going from London to New York to Sydney to Moscow to somewhere. Okay, so that's a piece of audio. I could, for example, say, make a spectrogram of that, and I should see me talking about those cities. Now, what I'm going to try to do is to say speech cases of line 117 of city. And if we're lucky, see what happens. See whether it will pick out what I was talking about. So this is now going and doing text to speech. It's trying to analyze, it's probably grinding my GPU here, trying to analyze that piece of speech. And I don't know why it's doing that. Okay, there we go. Okay. Oh, well, it got two of them. It didn't get all of them, but it got two of them. So that was picking out those cities. If I'd said, let me just for fun, let me just say, if I'd said to interpretation here, I think I would have gotten the actual entities. So if I'd wanted to have this, okay, I think it was previously it was probably loading up its neural net system, okay. Now what it should be doing is figuring out. Okay, there we go. So now these are entities, London and New York, and then I could go from the speech cases to actually something where I can do, you know, a geolist plot or some such other thing. Okay, let's see. Okay, so yeah, this is another question. Speaker match queue. I wonder if we have a sample speech by somebody. Well, let's see. Speaker match queue here. We could. All right. Let's see whether the example data male voice. It better not match. Okay, that's a piece of audio, and we say speaker match queue of the audio that I just recorded, and I'm pretty sure I'm not the sample here. So this better give this better say, oh, we got to download a neural net here. Okay. And then this will do an audio comparison. Obviously, this is relevant for recognizing audio in things. Now, by the way, I might say that I've been using this our speech-to-text system on multi-hour videos, actually, to get word clouds from those videos to get some sense of what was said in the video. And it's really useful, works really nicely. I mean, the actual transcript, if you looked at it, leaves much to be desired and has punctuation missing and things like that. But the sort of aggregated word cloud is highly useful. All right, let's see. Shadi, can you help me deal with video here?
Hi, yes.
So what should I do? I would like to show this example. What can I do?
So that's the beginning. We have the object going on.
No, I understand. I understand. I want to actually play this video. What do I do?
Oh, okay. Right click on the video that you see.
Okay.
And you can switch to a minimal or basic appearance. Maybe go to basic, which gives you all sorts of controls.
Okay. All right. Okay. This is what I was looking for. Okay. So now, hopefully this won't be too loud. Okay. How do I turn down volume? Okay. Stop listening to this terrifying. Why isn't that working?
Pause it. Maybe pause it.
Okay.
Now at least we can.
Did the llama cross the road is the real question. Okay, let's turn down the sound, and now, okay, it's a jolly little video here. Okay, now let's take that video and let's say video frame list of that video, and let's say I want 10 frames from that video. So there we go. So that just extracted 10 frames from the video. And if I wanted to, I could go and let's say I'd say just take let's call this video VD or something, and let's say extract. Let's say we extract. Well, let's actually extract 20 frames from the video. Let's live dangerously because I'm curious what's going to happen if I do this. And let's now just say feature space plot of those things, and let's just see what happens if I. So now I'm taking frames from this video and I'm going to feed those into machine learning. And okay, so that's so this might tell us a little bit about sort of the parts of the story. It seems like there's a part of the story where the llama is just hanging out. There's another part of the story where it's the credits and things. But that's so we can do that kind of thing. Okay, so now we can take this video and we can start doing operations on it. So for example, let's take instead of just taking a list of frames, let's say what is it called? Video frame map. Okay, so video frame map. And now let's say we want to let's try and extract something like the mean color from each frame of the video. So we're going to do that.
Video time series is the function. Frame map is the one that maps every frame to another image frame.
Fine. Yes, video time series. Okay. All right. So what this is going to do is it's going to compute as a time series on that video what is the mean. Okay, so that's the number of frames, probably 2,160 frames. That's the time steps. And now what I can do here is to say something like date list plot, and this is now going to give me the RGB values unfortunately, we didn't map it to red, green, and blue, so this is the default colors for my time series, but this is now giving me this is now doing analysis on that video. So it's showing me that, for example, at this point, we had, looks like things went to black. So we can start to do computations that are like the kinds of computations we would do for example, audio, but now it's for video. So for example, we might do something like, well, we could extract a frame from the video. We could, what's a good example here? We could, well, let's see what we have in video time series here. Maybe we can take, okay, here's another example. Let's just get the audio from that video. Okay, so this is now going to give us the audio from that video. If I wanted to, I could make a spectrogram of that. Might take a little, okay, there we go. Or we could, for example, what's a good thing to do on this video, on this audio? I don't think we're going to have much luck doing speech recognition. The llama didn't say anything. Oh, I tell you what we can do. Let's take on here, we've got some frames. Let me show you something else. So let's take these frames. Let's say we take that frame, and let's say we say find what am I trying to do? Find image text. So what that will do, oh, sorry, got to download the neural net it's going to use. That's going to try to identify where there is text on that in that frame. So I could also run this to try to figure out which frames in the video have text on them, for example. Okay, interesting. That's saying where in the image it found text. Actually, it'd be kind of interesting to just try doing text recognize on here, see whether we can take that piece of the video. This is what I get for having a new version today. It's neural nets are not fresh. Okay. So anyway, big new thing is video. Not only is there the question of analyzing existing videos, there's also generating videos. So for example, one thing I might do when this finally returns here is let me make a simple animation. Oh, come on. That wasn't good. I managed to kill it. Okay, well, doesn't matter. Let me make a simple animation. So let's say animate, let's say something like graphics of style disk yellow, style disk 00 T black, and then let me make that into graphics. There we go. Animate that with T goes from 0 to 1. Okay, so now this is hopefully going to make something like this. Okay, so now what we should be able to do, let's see if this works, is to take that animation and just say make a video of that animation. If we're lucky, okay. So it might take a little while to grind. Okay, so that's our video. So now if we do something like video frame list, 5 frames, for example, we should get, there we go. So now there's our video. We could take that video, we can export it in whatever format we want. We have about 200 or so of these video formats. What are they called? Video encoders. A horrifyingly long list of different kinds of, it's a giant zoo out there of video encoders, but we support a good chunk of them. So it should be good for lots of different uses of video. But anyway, it's kind of, this is ability to do that. So the question here about net encoders for video, we certainly have frame level net encoders. Do we yet have net encoders that work across frames? Maybe
we don't,
here.
But it's
coming. I mean, that was sort of the point of being able to do this. Now, there's a question here, can we do average shot length on the video? What is average shot length? What does that even mean? Is that well, kind of, if you can define it, we can. I mean, I'm sure what we can do. Okay, if we can really. Okay, so for example, once we've got a list of frames like this, so we could also do it. We could. Let's do this. Let's live really dangerously and do something which could be completely horrifying. But let's take our video frame list and let's say image identify across the video frame list, and let's see what we get. Okay, and there's a question here about videos with transparency. Let's see. Let's say 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 100%. 1 I don't know the answer to that. Is there an alpha channel in the video? Can there be an alpha channel in the video? Shadi, I think that must be for you because I don't know the answer.
I really don't know either. I don't know. I haven't come across
Should we try it?
one yet.
Let's try it. Okay, so this was that's funny. That was a list of the its best effort at identifying what was in bighorn sheep and so on is promising, but that's its kind of first level summary of what was in each of those frames. All right, let's just for fun, let's try. So what we could do here is to make this video out of something which is not, which has an alpha channel. And let's see whether that, how would we, let's see, if I do something like I say here, opacity, I don't know whether this will have, whether the background is transparent here, but let's do opacity 0.3 here, and let's just make the background to this. I don't actually know whether that background to that be transparent. All right, so let's see what this does. So that, oh, it doesn't like that at all. Oh, what did I do wrong? Oops, wrong way around. Sorry. I could do it like that, but I could also do this. Okay, so there's a lighter opacity, and the claim is that this is transparent. So we can, so now let's go ahead and do our video frame list of the video of this with video frames, 5 video frames, for example, and let's see whether we can, oh, it's going to export the whole video, then it's going to re-import and get 5 frames, which is kind of a goofy way to do it. But okay, now let's take these and let us do, how do we put these on top of each other? We could make a bunch of insets. We could say, take these graphics of inset. Gosh, I have to remember how inset works here.
Image compose also works, but the syntax, you got to take the first as the background and then put the other ones in the back.
No, what I wanted here was inset position. Okay, so I'm going to take of each object, and I'm going to take random real 10.2 as the position. I'm going to do this, and let's see what happens. That was not successful. Those did not show opacity, but that's possibly because the sort of the player is so far that's not successful. So I don't know whether this is going to work, but it's a good suggestion. All right, let's move on here. All right, we got a few things with face recognition, a few changes to rasterize, talking about some other things here. Oh yeah, that's a good idea. We can just do image measurements with transparency. All right, let's just try it. For the video frame list, I wonder whether that %9. Not transparent. Sorry. Okay. So, all right, we're changing topics here. We're talking about machine learning. We have a bunch of new capabilities for supporting, basically generative adversarial networks, being able to support GANs. We have a new NetGAN operator. Unfortunately, these are kind of complicated to set up, so it's not really easy to show a sort of a quick demo of this. But this is what you need to be doing adversarial training in a neural net. We're supporting some other things to allow for those kinds of capabilities. Another very practical thing is support for ONNX, for importing neural nets in ONNX format that allows us to get lots of neural nets from a variety of platforms like TensorFlow and so on. I noticed a bug here. That should be not boldface. Okay, here's one that is just a structural thing that sort of first came up in machine learning is categorical distribution. So if I say categorical distribution, and I say, for example, cat and dog, right? We can have a distribution which is a distribution of cats and dogs. So, for example, I might say, make me a list with random choices of make me 20 random choices of cats and dogs. Okay, so but now I want a statistical distribution that is that. So I can say, give me a categorical distribution of cats and dogs that is based on this, and I could say things like random variate from that distribution. And now if I say, give me 10 random variates, I'll get something. There's a lot of cats there. I get something like that. I can also, if I want to, I can say, I can ask for the PDF in that categorical distribution on line 14 of cats in there. And so the answer is it's 9 out of 29. Okay. Okay, so this is something that's useful as output from machine learning. It's a way of specifying probabilities for categorical objects. It's also useful, like in doing some quantum computing stuff recently. It's really useful for stating, this is the output. It's state A with probability such and such. And categorical distribution works not just for the scalar case, but for arbitrary arbitrary depth. So, for example, here we've got a ABC cross DE set of categories. Those are the weights there. So, and then we can say something like a PDF in that distribution of A and E, and that will give us the PDF for that. Okay. All right, let's turn to a completely different topic. We've been steadily making progress in computational chemistry. Lots of interesting things happening there. And will be a lot more in the future, but bunch of new chemistry formats, but one kind of cool thing, which is molecule recognize. So if you take a molecule, let's just do a web search. Let's do a web image search. What can we say? Molecular diagram. This may produce really crazy things, but let's see what it does. And let's okay. Not useful. All right, let's have a particular molecule. Let's say anybody got a favorite molecule? I'll tell you what. Let's do this. Let's say random entity. This is really living dangerously. Random entity chemical. This is like crazy. It's going to fail horribly because, okay, terbium penta. Well, we could just try searching that on the web. I think this is really doomed, but we can try it. Oops, that's not going to work. Let's say common name. Okay, I'll be amazed if this produces anything not completely ridiculous, but we can try it anyway. When did you ever meet a terbium compound? Great. Okay, somebody's got a favorite molecule. Let's try somebody's favorite molecule. It's interesting. Okay, I didn't know terbium had green powder stuff. Okay, anyway, let's see. Diagram. Let's try that. Nothing. Sorry. Well, let's try caffeine, but I have a very bad feeling that's going to be coffee beans and things like that. If this doesn't work, I'm just going to use I'm wrong. Okay, so that is an image, right? See that thing? It's an image. So we can take that image. We can it's an image. We can see its bits and so on. We can do it's an image. Okay, so let me now say molecule recognize, and let's see whether we can do kind of molecular OCR. And drum roll. Okay, that's looking promising. So now let's try, just to prove that, let's try molecule plot 3D of that. Okay, there we go. So what that did was it went from the image here, recognizing all these characters and so on, to an actual symbolic representation of the molecule, to something that we can compute with. So, if you have a paper or something and it's got pictures of molecules in it, now you can actually find what those molecules are. Okay, other things, various kinds of import formats, various, let me see, I wanted to talk about some other thing. Oh, okay, that's good. Keep going down here. Okay, well, another big thing that's happening is enhancements to data set. So in this version, the primary enhancements are let's do let's say the Titanic data set. The primary enhancements are to display. In future versions, there will be enhancements also to computation with these things. So what we're seeing here is, for example, we can say, let's do it here. We can say, take this column, and we can say, sort this column. So now I'm sorting by age here, these rows. Or we can say something like, here we can say, hide that column. Okay. And oops, I was just hiding that particular item there. I want to be able to hide the whole, oh, no, not what I wanted. Let's say I want to hide this column, hide column, there we go. So now that will hide that column. All right, so there are enhancements to display like that. There are also, at the level of the data set itself, there are now lots and lots of options for how the data set is rendered. So if I say max items goes to 5 or something, this will now display only 5 items there. If I start going in, I can kind of go wild, doing other kinds of operations on the to show. Let's see what I got here. All right, so this is an example of doing. Okay, that's getting a data set from the cloud. Let's just go ahead and get that. Permission denied. That's not a good sign. That's definitely not a good sign, since we're telling people to get that. Well, I think we found a bug here. Let's see. So that, no, permission denied. Okay, somebody's got to go fix that. Well, anyway, let's just take this data set here on line 30. And this is now saying, making various things. It's saying background, showing light blue and light orange, header background light green, let's say header background to purple, not a very good choice, but just to give a sense of what happens. And this is an item display function for the sex column here, and it's displaying these things like I could say something like M and F here, and now that will give me, that will determine that display. Okay, so a bunch of new things in data set. New kinds of options for headers and so on in data sets. Lots of things for making data sets easier to format nicely. Okay, here's a completely different thing that's coming. This is sort of an experimental thing that has been actually in the system for a decade, and we've never released it for a variety of reasons. This is kind of a spreadsheet view. And so now I'm able to enter things here in sort of very traditional spreadsheet type mode. So these are fixed width columns, and if I type too much, it'll just overlap. I could start typing a string. It'll be a string here. Okay, so now if I've got these columns, now if I evaluate this, what I'll get is, this is a table view, and it has this list inside. So if I say setting of that, I'll just get the list. But this is a control like something like a slider or something, and you can say make a dynamic. So for example, if I said table view dynamic of let's say tx here, that will now have that, and now I could say dynamic of tx down here, and okay, right now it's null, but now let me start putting things in here. Look at that. So now I can tab to the next thing. I've got and so now I've got down here a dynamically generated spreadsheet type view. Okay, and this comes with a variety of kind of convenient spreadsheety type things. I think if I take that, I probably can highlight that column. I could copy it. Let's see what happens to that. Oops, I'm just copying that whole thing there. But I can do a variety of things to this in a sort of traditional spreadsheet-like way. Select columns. I think I might be able to just, there we go. I just deleted that column and so on. Okay, so that's a new thing for data entry, basically, is table view. All right. Okay, here's something unexpected. So in version 12.0, we introduced the beginnings of our new sort of full symbolic compiler for Wolfram language. One of the spin-offs from that that's come in 12.1 is this new thing called data structure. And data structure is a kind of a representation of a raw data structure. So for example, let's go take a look. We've got, ooh, that isn't a link. That's really odd. Bug, guys. Oh, the link is down there. That's a bug. Okay, the whole thing should be a link. All right. So we got a bunch of data structures here. So let's say we say create data structure. And we say make us a linked list. Okay, this will be a linked list of length 0. Now I can say this linked list has various, so if I go to the linked list thing here, this linked list has various things that you can do with it. So let's call this the data structure ds. So now we can say ds of append, and let's say I say append random integer of I don't know, of 10 here. Okay, so now this will append a random integer to that data structure. Okay, so let's go do this 1,000 times. Okay, so that will now we've got this data structure ds. It's a linked list of length 1001. If we wanted to, we could say show me a visualization of that linked list. Okay, there it is. There's a visualization of the linked list. Now notice this is pretty fast. And if, for example, if I want to get, well, for a linked list, appending to the linked list is really fast. Now, if I wanted to, I could always say normal of ds, and then I will get a normal Wolfram language data structure out of there. But if I'm just accumulating things, I might be accumulating into my linked list just for fun. Let's go ahead and accumulate. Let's accumulate 1,000,000 elements into this linked list. Okay, boom, it's done. Here, let's just time that. Let's accumulate 10 million elements into the linked list. Okay, so this will run at basically full machine speed. Took 4.4 seconds to do that. Yes, and so somebody's asking the very good question, if you compile a linked list, will it compile to a native linked list? The answer is yes. And that's part of what this is all built for, is that the typed specification in the compiler can also deal with these new native data structures. Now, another thing that's interesting here is, notice in the documentation for this data structure, it says what the time is. So it says time of order n. So for example, here, if I say ds of length, sorry, this is a linked list. So that might not be so super fast because it's going to have to go through, 10 million elements. Oh, it was pretty fast actually. So this is running at sort of full machine speed. This is the implementation, I would say, of linked lists is actually in Wolfram language, but it is then compiled into raw machine code and runs at full speed. Let's see. yes, I mean the idea here. There's a couple of different things we're using this for. One is just optimal implementation of algorithms, and sort of optimal dovetailing of what is really fast to run at a machine code level. Sort of it's kind of a, and it also has a high degree of automation because you're able to take, for example, this linked list could have expressions in it. I mean, I could go ahead and I could start saying, I could make this linked list. Well, here, I'm sure if I just do that, I could append to this linked list. It's not going to object if I just append the expression, x squared to this linked list. It'll this thing, so that so you can make use of kind of all the Wolfram language capabilities, but sort of threaded through these kind of low-level data structures. Now let's take a look at a few of these data structures. We've got a variety of things. We're going to add, we've been curating, we curate movies, we curate chemicals. Now we're also curating data structures. And so, for example, here we've got, let's see, what's a nice exotic, well, we've got an AVL tree. Okay, so let's go ahead and let's create an AVL tree data structure just for fun here. And that's now a new data structure. So now let's go ahead and do insert into that tree. Again, I'm just going to say random. Let's just do a random integer 20. And let's do 50 inserts into the tree. And now let's say ds visualize. I don't know what this is going to do. I don't know what visualization, sorry. Okay, so that's now a visualization of our self-balancing tree there. And probably if I were to, and I could take that tree, I'm sure if I say normal of ds, it will actually turn it into, okay, it's turning it into that kind of data structure. So with this tree, for example, you can look in the documentation. It says various operations are order log n, and so on. So this is really useful for sort of running algorithms at maximum speed and so on. It's also useful if you're teaching a course about data structures. I would claim this is the best environment now for being able to teach about data structures and how they work. You can do all the various operations. You can immediately visualize in a notebook. You can immediately get the results to do computations on, make graphics on. I could measure timings here, and I could see how long things take, and so on. Let's see, you're asking about linked lists. Oh, well, we have both a linked list and a doubly linked list. So I'm sure if I did a doubly linked list, let's just do if I were to create a doubly linked list here, let's just do a few here, then I will have a different, see, the idea is if you've got a data structure, and please send them in doubly linked list. Now let's put 1,000 elements in there, and now let's say visualization. Okay, why does the doubly linked list not show itself with double pointers? That is kind of silly. That's really silly, isn't it? Why doesn't, I would have expected the doubly linked list would have arrows backwards and forwards. Well, whatever. But okay, so so that, for example, allows us to do fast insertions and things like this. Let's see. Yeah, we actually, this has sort of inspired us to try and provide some time complexity estimates for other operations in Wolfram language. I mean, the reason we haven't typically documented those in the past is because, we get a new algorithm, it's going to change. If, the time complexity of adding to a doubly linked list is never going to change. That's just a thing, a constant thing. Now we could look at a few other things here. I don't know, what do we got here? A Bloom filter, least recently used cache. I don't know. Let's look at the Bloom filter. I think the Bloom filter might have some fun visualizations. Let's see. Oh, I don't know. This bloom filter has operations in it that says things like you can say could contain X and so on. So for each type of data structure, there it's sort of standard operations are natively supported, and then you can build whatever you want in sort of higher level Wolfram language. Then you can also compile that higher level Wolfram language, preserving these low level data structures, and produce something that's fully compiled from that. So I'm excited about this. I think this really was kind of we knew there were going to be a lot of spin-offs from our compiler project. This is something that we realized we could do, and it's really neat. Okay, let's see. There's a question here about the video stuff. How much of the video feature set is available on the cloud? The answer is not. That is coming, I think, in a cloud release that is coming soon. The video player, I mean, you can do operations on videos, but the real-time playing of video is not yet available on the cloud. Let's try it. I'm now, see, this is what we get here. This is the dangerously living CEO story. Let's go ahead and let's go to the cloud version, and let's go to our cloud. Hold on, let me start it up here. Let's go to the cloud. Great, here we go. New notebook. All right. Now let me paste this in here. Oops, I need to, what do I do here? Do I go to view or do I go to magnification? I go 200%. Okay, let's see what happens if I do this. Not supported, sorry. Okay, that is coming soon, but it is not yet available. Okay, what about quantum data structures? Well, actually, our quantum computing package is doing really well, and we will have quantum data structures. The challenge of connecting them to a quantum computer is a different challenge. Now, of course, there is a little bit of a footnote to this because I've just been spending the last several months working on the fundamental theory of physics, and I actually understand what quantum mechanics is now for the first time ever. And I can tell you, I will be able to tell you a lot of really interesting things about quantum computers and what they can do and what they can't do based on that piece of insight. But hopefully I will be ready to talk about that in a couple of weeks. And I'd be interested in feedback actually from people because we're kind of almost ready now. But we don't want to be telling people about fundamental theory of physics when everybody is worrying about viruses and so on. Okay, so there's a question from Vergero. Sorry, I can't say the name properly. About weighted adjacency graphs and compiling them. So the interface between the graph system and the compiled data structures is interesting because our graph system doesn't really need compilation because it's already pretty efficient. It's already pretty much as efficient as it can be. Now, the interface between taking a data structure like a tree, for example, from this compiled data structure layer and putting it into the graph system, I think is decently developed, but probably not as developed as it's going to be. Oh yeah, by the way, I should mention that in the cloud, one of the things that you can do in the cloud that's actually easier than on the desktop is being able to embed videos in the cloud. So I can just take a video here and I can embed it in the cloud, and that's now a piece of cloud video that is embedded here. That's something, the whole sort of interface between that and our video computation capabilities is still a work in progress. Hopefully over the next few months that will be getting done. Okay, let me see. What am I not told you about? That is in version, Packlets. I want to tell you about that. Okay, here's a little bit of infrastructure stuff. So as some of you will know, we have a lot of support for blockchains. One new blockchain that we are supporting is the ARC blockchain. So if we say blockchain block data, let's say -1, blockchain base, arrow ARC, we should be able to find out what was the most recent block mined on the ARC blockchain, and we can do computations with that. Other kinds of things. Okay, another very practical thing is system credential. Okay, this is a kind of seems like a piece of boring infrastructure, but it's really useful. So what this is a thing that allows you to okay, so in your computer there will typically be a thing that is your system key ring, or it has different names and different operating systems, but this is now a direct interface to the system keychain. So if, for example, you need to authenticate on an external website, let's say you're using a Service Connect, and you want to do an authentication in the Service Connect, you will be able to use, that's not what I want there. Let's say I used URL read or something, and I'm doing an authentication to a website. I can use system credential, and I can then store my credentials, my login information, for example, directly in my system keychain, so that flows through securely into Wolfram language and out to the external website where you're doing authentication. So just a very practical thing that's very useful. Also being able to generate file signatures, some new things there. Let's see. Yes, okay, another new thing is ability to do, okay, let me show you another thing, is external storage. So external storage put, this is, so let me take a random thing. Let me take that picture on line 61. Okay, so this is going to go ahead by default and put that picture into IPFS, into, what is it, the interplanetary file system. That's a blockchain like public file system. So that now has that ID, and now this external storage object, it's now sitting out there, and it'll gradually get replicated in the world. And I could say external storage get. So this is a way of essentially putting things there. Now it just came back from IPFS. We have the same support for Dropbox. So you're able to put things out into Dropbox, including files and so on, and have them be accessible from your local Dropbox. Let's see. Oh, that's interesting. Point about the cloud, can someone fix the social sharing image so that when we post links to our cloud notebooks has a preview image? Okay, thanks for letting us know. I don't know that issue, but sounds like something to fix. Will the front end be faster for function suggestions? There's been some optimization done on that. I'm not exactly sure what the issue will be there. Okay, let's talk about other things that are just sort of part of the infrastructure. Another is we supported, as of version 12, access to external relational databases. That's been a system that has gradually been getting more and more built out. So for example, we have support now for Oracle databases. And by the way, that whole system credential thing is super useful for being able to store your database credentials. Also various operations like unioning, intersectioning of entity classes. So these are all things that are happening in the database. They're happening externally in the database rather than in the Wolfram language system, and then we're accessing them. So it can be very efficient. You can have a terabyte-sized database. It's the database that's actually doing those operations. Also, in terms of efficiency, some things with mail search and mail execute, being able to deal with mail on IMAP servers, that's another, and being able to do that in an efficient way but by using various kinds of caching. That's new to this version. Okay, let me talk about another big thing is the Packlet system. So some of you who've been users of ours for a long time may be aware of the fact that we have we have this thing called the Packlet system, which is a way of essentially encapsulating Wolfram language, or rather Wolfram system capabilities for people to be unfurled on a particular system. So for example, if you just want to define a function, store it, bring it back, you can just store it as you can just say save, and you can bring it back. It could be an MX file that will be a fast loading thing or whatever. That's just for a single function. If you want to nicely package your function, you might make it a private version of the function repository, the private function repository function, and so on. But that's for an individual function. What if you want to build a whole environment? What if you want to have something that brings up palettes? What if you want to have something that has documentation? All of those kinds of things. Well, then you can use a Packlet. And Packlets basically take whole directories of files. They use a Packlet info file that defines a manifest for how the Packlet works. And let me just show you to give some indication of what let's see here, of the kinds of things that happen with Packlets. So this is and the other important thing about Packlets is that they are auto-updating, or they can be set to be auto-updating. So whenever, in fact, a lot of the things when I'm showing things in the system and you're seeing, updating from server and so on, that's all happening through the Packlet system. Well, now the Packlet system is also accessible to users, and it's let's see, and that will be, right now we have a Packlet server, but I don't know whether this is yet available, but it will be soon. A kit for users to make Packlet servers. We are also planning to have a public Packlet server that will be kind of a public repository. So in the case of the function repository, just to kind of explain how that works, I create functions all the time that I think will be useful to other people, and they are put in the function repository. So for example, I don't know, let me show you an example to see if I can find something here. Sorry. It's just to tease a little bit of something else here. Let's see, we have, here's an example. This is a big complicated function that implements things called multi-way systems, which you would know about if you'd read the NKS book carefully. But so there's a lot of code here, and then there's lots of documentation, examples, et cetera, et cetera, et cetera. But the point is, this can then be deployed. I can either deploy it, I can either submit it to the repository, or I can deploy it, for example, locally on my computer or publicly in the cloud. If I deploy it publicly in the cloud, then if I give somebody the explicit URL for that function, anybody can use that function. So that's how it works in the function repository. In the case of Packlets, but if you want to, anybody can do it from your file system, from your cloud storage area. If you want people to be able to just refer to the function by name, then you have to submit it to the function repository, and then we're curating functions there. We've got about 1,200 functions now in the function repository, including some really cool stuff, including things that I suspect were contributed by people who are on this live stream, so thank you. So that's but in our policy for the Packlet repository is going to be quite different. The function repository is is a very much a curated thing. The Packlet server is going to be very much an uncurated thing, where people can put Packlets there and then give people links to those Packlets, and other people can download them, and it's much more a free-for-all type thing. The details of how that's going to work are still being worked out, but what's available now is the ability to use Packlets locally on your system, to be able to send Packlets to other people. So Packlets, ultimately, what is a Packlet? A Packlet is ultimately an archive file that has inside it all of those different assets that need to be installed in a system. And when you do a Packlet install, what it will do is it will take that archive file, unpack it, and, for example, set up the palettes, set up the documentation, etc. It will basically reach out and insert itself into the parts of the Wolfram system that it needs to insert itself into. Okay, so this has been a long requested feature, so I'm happy that we're able to deliver that now for version 12.1. And as I say, more coming with the actual policies for the Packlet server. Yes, it's operating like a Packlet manager. I'm being asked, do I check my mail in Mathematica now? I don't, and I probably should start doing that. And that's a very much a, I mean, I certainly have used our mail processing system to do bulk processing on my mail. And actually, because I've been working so hard on this physics project, my mail is unbelievably backed up and is in desperate need of bulk processing. And apologies to anybody here who's been somebody who sent me mail in the last few months. It's really backed up. Can you nest Packlets? Yes, absolutely, you can nest Packlets. Am I forgetting to say something about Packlets? I mean, I should say, what's the sort of trade-off between function repository and Packlets? Function repository, it's very well defined. Every function you get, it's just boom, you've got the function, it's going to work. In the case of the, I mean, you know, if I take let's say if I say resource function of, I don't know, string tuples, I don't know whether this one is yet publicly available, but yeah, I mean, it'll just work. It loaded the function, it's now loaded, it's just going to work. It's all very kind of straightforward. In the case of a Packlet, if you install a Packlet, it could change everything. It could make 2 + 2 be 5. It can do all kinds of stuff. And you're kind of entering a whole, you're potentially entering a whole new world when you install a Packlet. Now that can be good, or it can be confusing. And I think one of the things that actually we're doing actually for some of the tools that we'll be making available in connection with the physics project, the way those work is they actually have a Packlet in the back end, but they're exposed through the function repository. So what you'll see is a bunch of named functions in the function repository, but underneath they're all accessing code and a whole framework that's built using Packlets. Okay. Let's see, what have I forgotten to mention? Oh yeah, let me mention one other thing, the data repository. So we actually introduced the data repository in 2017, but it was really quite hard to contribute to it. And one of the things, because we basically asked you sort of upfront to do a lot of curation work. Now, what's interesting here is we just revised our we just revised our system for submitting to the data repository to make it much easier and to make it so that sort of in 5 minutes you can just take a data set, either submit it to the public data repository or just deploy it publicly in the cloud to be something that other people to whom you give the URL can access. Okay. All right, let's see. What have I forgotten? I think I've told you about most things of those. I'm sure I forgot something. I'm just going to have a quick look through, and then it's time for my dinner. Let's see. I told you about contour plots. I told you about vector plotting. I told you about mesh connectivity. I told you about data sets and table view. I told you about some of the new things in machine learning. There's also a lot of new actual neural nets in the neural net repository. They're just a bunch that arrived that were made possible by features in version 12.1. I told you a little bit about calculus of annotations. We didn't go into that in too much detail. More about how annotations work in images and things. We talked a little bit about equational predicate logic. We didn't really talk much about knowledge base. There are just, as always, a lot of new things on the knowledge base. I don't know why this particular one stood out for my blog, but yes, we also have breeds of goats now in the knowledge base. And oh, I forgot one important thing. Sorry, one important thing. I want to talk about external identifier. And then, two things I forgot. Sorry, two things I forgot. Okay. The first thing I forgot is new languages, new external languages. So we added support for Julia and Ruby and R. Let's see if I can actually run Julia here. I don't know if I can. I'm assuming that Julia allows you to do splat. Sorry. All right, let's try another one here. I would have thought that would have been configured here. Let's try Ruby. Let's see whether Ruby thinks the 3.7 is 10. That's good. Okay, but in any case, we now have the plumbing to support sort of standard data structures in Julia, Ruby, and R, as well as Python and JavaScript. More languages coming. We'd be interested in comments on that. The real challenge is being able to support in a good way the data structures of those languages and have them be interconvertible into our language. Actually, one thing to show here. Well, that wasn't a good thing to show. Okay, apparently this is how you define a function in Ruby. X times X, and boy, that looks like Algol from like 1968. Okay, but anyway, this is now an external function. So if I take that external function and I apply it to something, it will now run inside Ruby there. One thing that's coming that is being able to sandbox functions that are implemented in external languages. So the first one of those that's coming is Python sandboxing, and that will allow you to implement a function, for example, in the function repository, that's actually implemented in Python, but runs both in the desktop and in the cloud. And so it's as if you're just accessing it through the whole Wolfram language symbolic structure, but the actual code is running in Python. Let's see. TypeScript. Oh, there was also a question about Microsoft OneDrive. I believe we are going to be supporting a bunch of other storage systems now that we have Dropbox done. Let's see. Yeah, Haskell is underway. We're having some trouble because it requires some data type conversions and it requires some rather elaborate Haskell programming. And we have a very limited set of Haskell programmers, but I actually think we have mail out to one of the developers of Haskell. So hopefully we'll get some good answers there. Let's see. Question here was, how do you open a window for Ruby? Boy, I don't know. I mean, if you tell me a command that I can type in here, I can see whether Ruby will somehow magically open a window on my screen. Question about TypeScript in addition to Node. I don't know about that. So thank you. I mean, somebody will take that suggestion. How to install an R package for use in the external cell. I think that should work fine. I think that you can use external session in here, that this can be communicating with an external session, I believe, and that the external session can be preloaded. I believe that's all to do with the way that you configure the external evaluator, and I believe that should all work fine. Okay. External cell support for C++. Okay, well, we obviously have support through WSTP for C++. The main thing of interest there is supporting external functions and a library link system in C++, and we have some very nifty things underway for that. I think there was a discussion about doing it as an interactive thing, but I don't think that's really that interesting for C++, although it might be interesting to be able to show in a notebook some C++ code that you can then package up into an external function. Okay, SWSH, somebody can note your comment there. Okay, last but not least, I want to just mention the one last thing, which is Wikidata data and the concept of external identifier. So we have a lot of we have a lot of ability to talk about entities in let's say we can talk about, I don't know, Alan Turing as an entity, and that is a symbolic entity in our in our system. Okay, but there are external there are, by the way, people are asking about weird languages. And I will say that one of the projects we have underway is a thing for making virtual machines. And that will probably be the way that we support these weird languages that are the virtual machines that we're building are initially things like virtual machines for the blockchains, but we're also going to have sort of minimal virtual machines for Turing machines, and we obviously have a Turing machine function right now, but for register machines, things like that. Okay, back to this external identifier. So there's the notion of sort of external identifiers that are well-defined things in the world, but we don't necessarily have a concept for them. So we now have this notion of external identifiers. We have an increasing number of external identifier types, which are things where we provide sort of curated access to those kinds of external objects. So an archive ID, ISBN for books, an INCHI ID for chemicals, a Music Brains ID for music works, all kinds of things like that. Okay, so one particular area that's interesting is Wikidata. So Wikidata has, and so we have this notion of Wikidata data. So for example, I can say, let's take Alan Turing, and let's say I want Wikidata data about, let's see if we can do this. I don't know if this is going to work, whether birth date is a property in Wikidata, but we could ask about, okay, there we go. So that's now querying the Wikidata system for a birth date for Alan Turing. So for example, we could do something like this. We can say, let's search Wikidata for hoaxes. Okay, so these are various different things that are features of, well, I guess that one of these things is an entity class that we can pick up one of these. I think if we click on that, what's it going to show us? Okay, label, description. So that's an external identifier. I mean, this is unfortunately, as soon as you go into the world of data we didn't curate, we are profoundly not responsible for it. And I have no idea whether it's correct, whether it's but so this is the entity class, but you can use all of our capabilities for querying the entity system, all of our kind of things related to Sparkle and so on. So this is now asking for the entity class of hoaxes. This is looking at the Wikidata IDs for all of those things that it considers to be hoaxes. The 1967 British flying saucer hoax. You know, I think I remember that one. Huh. Okay. So let's say, for example, I don't know whether we can look here. This is giving us, oh, sorry, this is not, this is now going to give us which of the Wikidata entries about hoaxes has a coordinate location, and then plot a map of those. I think there was one fun one here that I had in the blog that was about, let's see, what is this? This is, I'm just doing evaluate in place to get something that shows me those nice boxes. So this is saying in the Wikidata, what is this saying? This is in all of Wikidata, this is studied, this is asking for things which are the opposite of studied by philosophy. This may give complete garbage. What on earth is this? This says a physical object, the opposite is an abstract being or a mental object. But I don't know what this is. If I do here something like, I mean, I'm sort of tempted to fill in here something like hoax, and I have no idea whether that's going to do anything. It's probably going to say, oh, there's nothing there. So if I, instead of saying studied by, if I just say, so this is asking for a property of everything in Wikidata that it was studied by, let's see what happens if I do something like, let's say Wikidata search, and let's say physics, for example. See what happens here. Actually, now I'm really curious. What happens if I say, is that going to do anything? No fundamental theory of physics in Wikidata. But if we take one of these, and I don't know what it is, and it might be, who knows what that is, but let's see if we say Wikidata studied by physics. Okay, so this is saying these are things studied by physics which have the property opposite of. So again, this has, so physical phenomenon, they're saying the opposite is a simulation. I don't know about these opposites. The opposite of experimental physics is applied physics. Unconvincing. But anyway, these are things, actually, now I'm curious what happens if I were to just say Wikidata data, show me as an association the, well, it's just actually a, let's see, Wikidata data, oops, I just want to say that as an association. So this is all things studied by physics, according to, oh my gosh, there's a bunch of weird stuff here. All right, this is probably where we wrap up, because these are all things that, according to Wikidata, are studied by uses, studied by physics experiment. Whatever that means, who knows? Okay, so now we're diving. Oh, that's kind of cool. That is actually showing a formula. Okay, well, we're diving into a morass of uncurated data. But what's important here is that we've got a sort of symbolic way to explore this data and see what can be found in it. Okay, there's a question here about syntax highlighting for external languages. We're well aware of that issue. It is more complicated than you think because it involves kind of supporting different styles of editing inside notebooks. It actually will probably come to the cloud before it comes to the desktop, but that we hope will be coming fairly soon. All right, we should wrap up in just a moment here, but if there are any other questions, there's a question about the summer school that we do every year. We're definitely intending to do it in some form or another. We don't yet know exactly what form because of those pesky viruses out there. We hope, yeah. All right. Well, thanks for joining us, and you can download version 12.1. You can, if you are running in the cloud, you will already be able to immediately access. If I go over to the cloud here, and I say what version are you running, it should say it is running 12.1. There it is. So thanks all for coming. Enjoy 12.1. I am greatly looking forward to talking about physics, which I hope to be able to do in another week or two. Thanks all very much. Bye.